So now we're actually going to put some numbers to the strength of an acid or a base. So we have strong, weak, and negligible acids and bases. We have been looking at the transfer of an H plus, like everything has looked at H plus and it's coming or going, connecting to or getting released from a molecule. And that is what we're looking at as in terms of how acidic or basic something is, its ability to interact with H plus. So as such, we are going to look at the pH scale, which looks at the concentration of H plus. It's kind of a measure of how acidic something is. So pH is defined as the negative base log 10 of the concentration of hydronium atoms, or H plus. So we could also write it as pH is equal to negative log concentration of H plus. So the more H plus, right, the more concentrated we're actually, the more acidic something is going to be. So the scale is used for convenience. It's a logarithmic scale. So you have to recognize that this is every order of magnitude, or it's by orders of magnitude. So the scale goes from 0 to 14. It never gets to 0, never reaches 14. It's kind of a lie, it can, but in some very specific circumstances. But the pH scale is from 0 to 14. By the way, we have seen this number before. And so where have we seen this number before? Well, we'll see it just a second. So the scale is used for convenience. It's just easier to talk about a number as opposed to like, and well, you'll see in just a second. So in pure water, we know that Kw is equal to the concentration of H plus times the concentration of OH minus. And we know at 25 degrees Celsius, that value is 1 times 10 to the negative 14. And let's start right there with that. What we do notice is, look at that, our pH value goes to 14. There is the max, right? pH max of 14. So we do in fact have that 14, like that's where the scale comes from. It's the autoionization of water. All right, so in pure water, we know that this is true. Concentration of H plus times OH minus is equal to 1 times 10 to the negative 14. Again, this is nothing more, this right here is nothing more than a equilibrium value, right? Conversion of water into its ions. So, and since we know so since these two are essentially equal to one another, right? So Kw is equal to, sorry, let me say it again. If I have a water molecule and it spends half of, and it separates into H plus and OH minus, that means for every one water molecule, I divide it into one H plus and one OH minus, meaning that those two things are equal to each other. Right. So what this means is we have each of those could be assigned X, right? Concentration, if this is X, this is X, this is X. So for every H plus, I'm also getting an OH minus. So we can solve for the pH at equilibrium. So X squared, which is equal to 1.0 times 10 to the negative 14. If I take the square root of both sides of this, we find out that X, therefore in pure water, X is equal to 1 times 10 to the negative 7. That's what we find by doing that math, which is equal to, because X is equal to the same thing, 1.0 times 10 to the negative 7 is the concentration of H plus and the concentration of OH minus. So basically solving for X gives us the concentration of H plus. By the way, whenever you're doing this, whenever you have, let me just actually highlight, let me get rid of that. Let me just highlight. When you know the concentration of H plus, this is what we're looking for in order to get what we call pH, in order to get like how acidic or basic it is. The important point here is this little value. This is always a good approximation of pH. So the exponent there is going to be a good approximation of your pH if it's the concentration of H plus. So let's take this one step further. And since we know that pH is equal to the negative log of the concentration of H plus, we can plug in our concentration of H plus, which is 1 times 10 to the negative 7. We end up with a pH of 7.00. This is the neutral pH. This right here is the neutral pH. It's neutral because that's water splitting into its parts, right? So that is the neutral pH. Well, it turns out in terms of acidity and basicity, if we have more H plus present, we have more acid present. So pH is anything less than 7 is acidic, greater than 7 is basic. Simple enough, okay? Again, it's important to know as concentration of H plus increases, the pH is going to actually see a decrease. pH decreases as concentration of H plus increases, pH decreases. So they're inversely proportional. But again, if you look at concentration of H plus, when it's 10 to the negative 7, pH is equal to 7. When the concentration of H plus is equal to 10 to the negative 3rd, pH is equal to 3. So this is 4 points different. The delta of this is 4, right? The delta of this, though, is actually what? 10,000. Okay, so just recognize that there is a big difference there. It's a logarithmic scale for a reason. So one change in pH is actually 10 times as much in terms of acidity, okay? So just to give you an idea of what the concentrations are, of pH levels, stomach acid is super acidic, lemon juice, cola wine water. By the way, milk is slightly acidic. People typically think that it is basic. It's not, it's slightly acidic. Human blood is actually slightly basic. Borax, something we're going to use later. Seawater is slightly basic, although slowly getting acidic, sadly. And yeah, so you can see all of the different acidity versus basicity. By the way, what you'll notice is these values are always going to add up to 14, and we're going to look at that later. So -1, -13, 14, 3 and 11, 14, 8, and 6. So if you know one, you know the other, and we'll talk about that. This pH scale is something that we're going to talk about a lot, or this P scale is something we're going to talk about. So pH is negative log concentration of H plus. We're also going to talk about pOH. pOH is the negative log of concentration of OH minus. Okay. We do something called P. There's some thing you look at called PI, which is actually the negative log of the concentration of I minus. Oh, that's a titration that you do. What do you think PK is? That's right. It's the negative log of the K value. So equilibrium. In fact, we do this quite a bit. So this one's going to be important a bit later. Well, somewhat important a bit later. These are absolutely important. Just recognize this lowercase p followed by something is just the negative log of whatever that thing is. Okay. This right here is the most important thing that we're going to look at in terms of doing these calculations. If you know this, your life is significantly easier. I'm going to have two sides to this. In fact, I think I can probably highlight it. I'm going to have to take a second here. So this side over here is our acidic side, okay? Both of those things. pH is measuring acidity, and yeah, so pH is measuring acidity, H plus is the concentration of acidity. So this is the acid side. Okay, so if I want to convert between the concentration of H plus to pH, we already know that that is pH is equal to the negative log concentration of H plus. That's how I convert from H plus to pH. Or if I want to go the other way, I will just take the 10, I will raise both sides to 10, right? So I'll do the inverse log. So 10 raised to the negative pH is equal to the concentration of H plus if I'm looking for the concentration of H plus. So there, we've got the two tools we need to convert back and forth between H plus and pOH or and pH. Okay. Next up, this side over here, is the basic side of things. So the basic side of things, it's the same set of equations. pOH is equal to negative log concentration of OH minus, or 10 raised to the negative pOH is equal to concentration of OH minus. There we go. So we have the equations that can convert back and forth between those two. In the middle, we have water. Actually, it's difficult. We have water in the middle. Okay, so in the middle, we're going to have water. So water is kind of both acidic and basic. It's going to have Kw is equal to the concentration of H plus, concentration of OH minus is equal to 1 times 10 to the negative 14. Okay, so we have essentially a way to convert back and forth between OH and OH minus and H plus through this equation here. Or we can actually convert back and forth between pH and pOH, because pH and pOH, just as I spoke about earlier, is equal to 14.00. So this is an important set to know. You should know each of these. Maybe it looks a little bit confusing, so I'm going to erase that one. But again, converting back and forth, we're going to use this quite a bit, know how to do these conversions. We're going to do a handful of examples, but you should be able to do these calculations. So a lot of the times you would be given a pH and asked to solve for something here. So you would go this way then that way, or this way then that way. Sometimes you're given H plus and you're asked to solve for pH. Sometimes you're given H plus and asked to solve for what the pOH is. So there's any number of things, but if you have this set of equations, you can take any path that you need, okay? Great. Okay, this is the summary of the acid equations. We're going to use these later, so just know those. How do we measure pH? It's important to just talk about how we do it in lab. So litmus paper is basically going to tell you if it's red turns blue, blue turns red. So blue tells you if it's acidic, red tells you if it's basic, but it's very binary. It's either it is below 8 or above 8. It's above 5 or it's below 5. We have a handful of acid-base indicators that change colors based on the pH. We use phenolphthalein a lot to tell you if things like start to become pink at around a pH of 8. Okay, so there's a bunch of different methods that we use. The most accurate is a pH meter that actually measures voltage. But ultimately, all of these will lead to some version of us getting a pH. So if we only care if we need to make it basic, we don't care how basic, we would use litmus paper. If we need to be pretty precise, you happen to have an indicator that's exactly where you need it, you need one of these, but a pH meter is always kind of perfect. So the indicators are more rough when you need them to be, and the indicators are more rough when you need them to be, and the paper is for when you get less rough than that. Okay, so with that said, we're going to start talking about, we're going to do a couple of calculations, but there are 7 strong acids, just to remind you. There are 7 strong acids. Those are the ones you need to know. There's no, just got to know them. They're all in the same location in the periodic table. We talked about them a bunch, so you need to know those. If it is not a strong acid, it is going to be considered a weak acid. Again, we recognize a weak acid by having H first, and it's not one of those 7, or you see this group, COOH, which often is seen as CO2H. Either of those would indicate, oh, that's an organic acid, that is a weak acid as well. Strong electrolytes completely exist totally as ions, right? They're completely product favored. So H3O, so 0% of this exists, 100% of the product exists. Acids can be monoprotic, diprotic, or polyprotic. Protic, that just means proton. So monoprotic means it donates 1 H plus. Diprotic means it donates 2 H pluses, and polyprotic, it donates 2 or more, because you can actually call a diprotic a polyprotic, because technically it is. Okay, so here's some polyprotic acids that you have. What you'll notice is each of these has more than 1 hydrogen out front. Even like if you look at this one right here, malonic acid, it does have a hydrogen. These hydrogens are not acidic. These two are, because they're out front. Those are not. Okay. And then let me just quickly show you a regular. So this is acetic acid. And I have shown you this before another time, but this is acetic acid. What you'll notice is this proton right here is the acidic one. It's always the thing attached to something super electronegative, because what you can imagine is if I have a water molecule, I'm going to flip this around actually. If I have a water molecule and it's got these lone pairs here, and we know that this thing is pretty electronegative. We know it's pretty negative around the top. So this is going to create a bond with that hydrogen. Well, because the electrons are being pulled away from this hydrogen, what you end up seeing is these electrons easily get pulled toward that oxygen, and we create this really stable, and some other stuff happens, but ultimately what you end up with is you end up with the H3O plus, right? Which is, I guess it should be purple because that's what it was, H3O plus. And then you have what's left is those electrons from that bond are now on that oxygen. And that's what we've got. So this is what we typically form, that carboxylate. So this is carboxylic acid. And this is called a carboxylate. Those are the, just quickly, I just want you to recognize that those are the organic acids. That's the COOH. Yeah, that's the COOH group, or CO2H group that I was just talking about. Anyway, polyprotic, different product. You got to recognize the ones out front are the ones that are acidic. Okay, moving on. So here's a question. What is the pH of a 0.01 molar solution of HNO3? So first of all, HNO3 is a strong monoprotic acid, so it completely ionizes. Again, even though we know what this is going to be, we are going to write it out in terms of what its equation is. HNO3 forms H plus and NO3 minus. So if I start with a concentration of 0.01 molar HNO3, so for every one of these, I'm getting 1 H plus and 1 NO3 minus. My concentration of H plus is 0.01 molar and 0.01 molar of NO3 minus. And again, all I'm really interested in is if we can figure out the concentration of H plus, we can figure out the pH. There's that. So I'm just going to use green. So pH is equal to negative log concentration of H plus, right? Which is equal to negative log 0.01 molar, which is equal to 2.00. That is the pH of my compound. This gets more complex for polyprotics, but actually not much more complex when it comes to strong polyprotics. So that's strong bases, strong acids. They completely ionize. So we just have to kind of do the stoichiometry to figure out how much H plus I end up with. Strong bases are, again, just as a reminder, are the soluble hydroxides, which are NaOH, KOH, and the heavy alkali earth. So that's the list. Okay. NaOH, KOH, basically LiOH. So basically the soluble hydroxides, alkali metals. It's not just these, that's kind of a misnomer. So it's group 1 and OH minus plus the heavy group 2s. So like strong acids, they are going to completely dissociate. So NaOH again, so for every, I have 0% of this and I have 100% of this. So determine the pH of a 0.001 molar solution of NaOH. All right, we can do that. So let's see here. So for A, if I have a 0.001 molar, so first thing I'm going to do, NaOH. We don't know if it's, well, we do know it's not in equilibrium, so I don't have to do a double-sided arrow because it's a strong base. Na plus and OH minus. I know that I have 0.001 molar NaOH, means I have 0.001 molar this of the Na plus and 0.001 molar of the OH minus. And so again, do we have H plus? We don't have H plus, but what we can focus on is we can focus on this. Because OH minus happens to sit in our wonderful little box here. So I am given OH minus. I would write this down separately and have it because you're going to get used to using it. So we happen to have the concentration of OH minus we need to get here. So how do we do it? So we have two choices. I go over and down, or I go down and over. Okay, so I'll do it one way, and then for the second example here, I'm going to do it the second. So yeah, so let's see here. So we have so what I know is the concentration of OH minus of the solution is at equilibrium is 0.001 molar. Okay, so the concentration of H plus times concentration of OH minus is equal to 1 times 10 to the negative 14. So the concentration of H plus is equal to 1 times 10 to the negative 14, all divided by the concentration of OH minus, which is equal to, one more time, times 10 to the negative 14, all over 0.001 molar. Turns out the concentration of H plus is equal to 1 times 10 to the negative 11th. And now we're simply just going to plug this in. pH is equal to negative log concentration of H plus, which is equal to negative log 1 times 10 to the negative 11. pH is equal to 11. And of course, we always want to check and see if it makes chemical sense. Does it make chemical sense? Yes, it does. It is basic. The pH is basic. So we are good to go. There we go. All right. How about B? So this was A. How about B? So I would pause it and see if you can figure out, but I'm going to do it on my own here, or I'm going to do it. So pause it and figure it out and then go from there. Okay. This one's a little bit different. This is a strong base, CaOH completely dissociates into Ca2 plus and 2 OH minuses. So that means if the concentration is 0.001 molar, I know that I end up with 1 calcium, but I actually end up with 2 OH minuses. So make sure you get that sorted. So that means the concentration of OH minus at equilibrium is equal to 0.002 molar. Okay. So now I'm going to do this one the other way. So pOH is equal to negative log concentration of I'm just going to do it the long way. Concentration of OH minus, which is equal to negative log 0.002 molar. pOH ends up equaling 2.70. Okay, and then pH plus pOH, and again, these equations I'm getting from the little box up top, is equal to 14. So I'm going to rearrange that. pH is equal to 14 minus pOH, which is equal to 14 minus 2.70, right? pH is equal to 11.30. So now it is not that far. It doesn't seem all that different, but remember, this is a logarithmic scale. So although it doesn't seem too much different, that actually is, it's not just, 0.3 different. It's pretty big, but still double the concentration. The pH doesn't change that much, but it actually does. That's quite a bit more. So yeah, good. So does the number make sense? Yes, it's basic. This thing is basic. We're good to go. We have that sorted. All right. Now we're going to start looking at some of these calculations. And in fact, I'm going to pause it here and I'm going to create a new video, I think, for dissociations and determining K values. So the next video is going to be looking at determining weak acid-base calculations. So weak acid-base calculations is going to be next because this is pretty intense. So we'll just call it stop there.